Okay, in this video, let's try to finish section 5.2 and continue with section 5.3. So, recall from section 5.1 where I got you the curve, and we estimate the area under the curve by divide the interval into a sub intervals, and then we estimate the rectangle here using, in this case we're using the right endpoint. If you are using the right endpoint, then you go from right to left to make your rectangle. So in this case we using this rectangle here, 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 and here, then we sum all of them together to get the area. And obviously you can see from here your rectangle is bigger than the curve. You have some extra spaces here, and therefore your answer would be somewhat overestimate comparing with the true value. Now by cutting these intervals smaller and smaller, right? Smaller and smaller, we will get a better estimate for the area, because the extra spaces here become smaller and smaller approaching to the curve, and therefore we don't have much extra value above the curve. So let's go over one more example, and hopefully it will make sense to you. Let's go to the next page for one more example. Now, considering that I have the function f of t equal 3 t minus 5 and then x squared. Now, this represents the rate of change of some quantity, so the rate of change of something, okay? And we can estimate the total change from the time t equals 0 to t equals 4. Okay, alright, using multiple rectangle. Okay, so if you graph this on the xy plane, you should have something equal to this one. So here we have 80, 60, 40, 20. So 60, 40, and then 20. Then we have 1, 2, 3, 4, 5. 4 and 1 and then 0, 2, 3. Okay. So if you have 0, so if you graph this one, if you have 5, right, 5 t equals 5, then 5 minus 5 is 0. 0 times 3 is 0. So at the time t equals 5, you have 0. At the time t equals 0, you have minus 5 squared, which is 25. 25 times 3, that's 75. So it's around here. At 1, you have 1 minus 5, which is minus 4, and minus 4 squared, that gives you 16. 16 times 3, that's 48. So it should be around here. And at 2 minus 5 is minus 3. Minus 3 squared, and then that gives you 9. 9 times 3 is 27. So 27 is around here. And 3 minus 5 is minus 2. Minus 2 squared, that gives you 4. 4 times 3, that's 12. So it should be around here. And 4 minus 5 minus 1 minus 1 square, that's 1. 1 times 3 is 3. So very close to 0. So we can draw the graph something like that. Okay. Now we only want to estimate the total change. That means the area under the curve from the time t equals 0, which is here, to t equals 4, right? So at this point only. Okay. And we can do this by using two ways, the left and the right hand sum. So let's do the left hand sum first. So the left from 0 to 4. So the left hand sum, that means we start from 0, the leftmost endpoint. Okay, so from 0 I go up to the y-axis. I got 75 here, and then because we are using, in this case we are using 4 rectangle, right? 4 rectangle. So 0 to 1 is 1 rectangle, 1 to 2, 2 to 3, and 3 to 4. Now from 0 we are using the leftmost endpoint for the left hand sum. From 0 I have this point, and then I'm using the left endpoint, so I draw from left to right to make my rectangle. Okay, and then the next point is 1, so I go up to the y-axis. I draw to the right, and then I draw my rectangle. And then from 2 I go up to here, I go to the right, I draw my rectangle. From 3 I go up to the 4, I draw to the right and make my rectangle. So I have 1 rectangle here, 1 here, 1 here, and then 1 here. I have a total of 4 rectangles. And using the leftmost endpoint, we have the left hand sum. That means we don't use the point when t equals 4. We use 0, 1, 2, 3 for the left hand sum, and we ignore the last right hand point, because we only have 4 rectangles. Now you see that we have the extra spaces above the curve. Therefore your left hand sum will give you some value that is bigger than the true value. Okay, so let's estimate the area here. The area is the height times the width, right? So let's do that. So the width is always 1 unit, right? 1 to 2 is 1, 0 to 1 is 1, so it's always 1. Okay, so we always have the width to be 1. The length, the height, is the value of the y-axis. Okay, so the first rectangle here, the width is 1, and multiplied by the height here, which is 75. Or you have f of 0, because this is the f of t, right? So when t is 0, we have the height. So f of 0 multiplied by 1, and we add to the next rectangle here, which is f of 1. Also the width is 1, the height is f of 1, because we take this value as the 1. So f of 1, and we add to again f of 2 for the height of this one. So f of 2, and the last one would be f of 3 multiplied by 1. And of course we have 1, f of 0 is 75, and f of 1 here is 48, and f of 2 here is 27. So 1, 27, and the last one is just 1. I mean 12. Sorry, yeah, 12. Okay. So if you do all the summing together, you get 162. That's for your left hand sum. Now let's do the right hand sum. So if you do the right hand sum, we skip the leftmost point, end point. we skip the first one, we move to this one. So we start from 1. So from 1 we have this point, right? Because we are using the right hand point, right hand sum. So we go from right to left to make your rectangle. So I go from right to left to make my rectangle. This is my first one here. Okay. Now the next point is a 2. From 2 I go from right to left to make my rectangle. From 3 I go up here, I go to the left to make my rectangle. And from 4 I go up here, I go to the left to make my rectangle. So you see here, the right hand sum give me the rectangles that are smaller than the curve or under the curve. Therefore the true value of the curve should be bigger than the right hand sum. So again, I'm using the point 2, 1, 2, 3, 4. Before I use 0, 1, 2, 3. Now the right hand sum I use 1, 2, 3, 4. I skip the first one and then I move up until I got 4 rectangles. Okay, so let's do the summing. Again, the width is still 1 unit, right? And the first height is f of 1. And then the next one is f of 2. Remember, before we started with f of 0, now we start at f of 1. So f of 2 plus f of 3 plus 1 f of 4. And if you do all the summing, you should get 90. Now, the right hand sum and the left hand sum, your true value should lie some number between 90 and 162. In fact, you can estimate this by summing the right and the left hand sum and divide by 2, 126. So the estimate value for the area under the curve is around 126. So we add the left and the right hand sum. We divide that by 2. So before, as we can see, we estimate the area under the curve using 1, 2, 3, 4, right? 1, 2, 3, 4 rectangle. Now, in order to have a better estimation, you should divide this into maybe another half. So 1, 2, 3, 4. So we have a total of 8 more. I mean a total of 8 rectangle. And because we are using the, for example, let's use the left hand sum, right? I draw from left to right and make my rectangle. So I have 8 rectangle now. And remember, the extra spaces now are getting smaller and getting closer to the curve. Comparing to here, we have bigger spaces because my rectangle is, the width is big, it's 1 unit, but now it's just half and we got smaller extra spaces. And at some point we will even divide this into smaller rectangle. So we have 8 and now we have divide that into half. We have 16 rectangle. It's very, very small rectangle adding together. And it's convenient if we use the notation of the Riemann sum to represent the value of this rectangle adding together. So let's try to rewrite this as a Riemann sum. Okay, so if I'm using the left hand sum, right, I will have I from 1 and I go up to n, f of ti and delta t. Okay, this is the right hand sum. So we start from f of t of 1 and then we go up to n. So for example, in the previous case, we have from 0 to 4. So that means we go from 1 to 4, right? From 1 to 4 for the right hand sum. Now for the left hand sum, we go from 0, right? We go from 0, but we do not include the last point, so we go up to n minus 1. F of t I and delta t. This is the width before, right? The unit of the width. And this is just the height, or the value of the vertical column, right? The height. So we use this to represent the summing of all of these value, right? We're summing them together. So this notation is just the sum, the summation formula, summation notation. We sum all the value together. And delta t usually is the unit of the rectangle, the width of the rectangle, and we take b minus a divided by n. That means we take the interval from the max value at 4, we minus 0, the two endpoints, minus each other, and then divide by the number of the rectangles that you want to. And ti is easy, just equal to a leftmost endpoint. So here is a, and here is b, right? So we stack from a, we add to I and delta t. So if I is 0, we have only t of 0 with just 0, right? If I is 1, we have a plus 1 multiplied by delta t. That means we are here, we are from 0, then we add delta t, we go up to 1, and therefore t of 1 is at this point. We just keep moving forward. Okay, so let's move on. Because as the number of rectangles rolling faster, when we want to have a better estimation of the area under the curve, sometimes the number of the rectangle, or n, can go up to infinity. That means we have too many rectangles that are very small in the width, and it's really hard to see with your eyes. And we define that to be the definite integral of f from a to b. Okay, so when the rectangles becoming extremely huge, then we call that to be the definite integral of the function f. That means the function of the curve from the left endpoint a to the right endpoint b, and you can write that as this notation. So this is just like the s, letter s, but it's expanding in the vertical axis, right? So f of t dt. So this one is the definition of the definite integral. N I equal 1 f of ti delta t. Now again, delta t is just a right endpoint minus a left endpoint divided by the number of the rectangles. So before, we summing all the value together, but when the limit of this summation formula, when n approaching to infinity, the whole thing here, we can rewrite this as the definite integral. So this one represents the value of the area when n is approaching to infinity, and we have f of t And dt, this one again is a width. We're not using delta anymore, but we're using d to represent for the width, dt, and f of t from a to b. So this one is called the definite integral of the function f from a to b. Okay, so let's do one example, and hopefully it will make more sense. So I have the value of x, and here is f of x. I have 0, 5, 10, 15, 20, 25, and the value is 100. 82, 69, 60, 53, and 49. Okay, and we want to estimate the definite integral from 0 to 25 f of x and dx. Okay, so again, this one is just the sum, right? The sum of the rectangles from 0 to 25 on the x-axis. Okay, so we have, again, this is 0, 25. So this is the sum of all of the value from 0 to 25. Now we have 1, 2, 3, 4, 5, 6. So from this table we know that we have 6 data points, right? If you have 6 data points, you should have 5 intervals, or your n equal 5, or you have 5 rectangles. Again, count the number of the data points, subtract 1 from that, you will get the number of rectangles you should have for your sum. And if you know here, from 0 to 5 it's 5 units, 5 to 10 it's 5 units, 10 to 15 it's 5 units. So your delta t, in this case, because we are using x, so my delta x is 5. Because the distance of the width of my rectangles is 5. From 0 to 5 it's 5, 5 to 10 is 5. So it's equally spaces, so it's 5. So each interval has a width of 5. Now we can calculate the left hand sum. So this is left hand sum. Okay, so if you are using the left hand sum, we start from the leftmost end point and data point. The leftmost and the data point is this one, and we go from 1, 2, 3, 4, 5. We stop here because we have 5 rectangles. We go from the leftmost end point, 1, 2, 3, 4, 5. We stop right here. Okay, so let's do that. The first point, remember, the rectangle, this is the width, and this is the value of f of x for the height, right? So the width is always to be 5, and the first point, the first height, is the first one of 0, is 100. Then we add to the next one, the width is also high, it's also 5, and we multiply by 82, and again 5 multiply by 69, again 5 multiply by 60, and then plus 5 multiply the last end point, or 53. So if you sum all of them together, you should get 1820. Okay, now we are using the left hand sum. How about the right hand sum? So the right hand sum, we start from the second point, right? The second point all the way to the last one. We skip the first point in the data set, we go all the way to the end. So 1, 2, 3, 4, 5. Again, 5 rectangles. So again, the width is also 5. Multiplied by the first point is 82. And 5, 69. Plus 5 multiplied by 60. Plus 5, 53. Plus 5, 49. And that should give us 1565. Okay. So we have the left hand sum and the right hand sum. Now, to estimate this, we just take the left hand sum, we add to the right hand sum. Right? The left plus the right all the way divided by 2. And that should give me 1692.5. So the estimation of this definite integral is just the arithmetic value of the left hand sum and the right hand sum. So take the two values, adding them together, and divide that by 2. Okay, so that is the end of 5.2. So let's now move on to section 5.3, the definite. Again, we're gonna learn about the definite integral as area. Okay. So when f of x is bigger than 0, the value of the definite integral from a to b, f of x dx, again dx is the small value of x, or the width, is equal to the area between the curve and the x-axis from A to B. Okay, so when your f of x is positive or is above the x-axis, this value here, the definite integral of f of x dx from A to B, is actually the area under the curve between the curve and the x-axis from the point A to B. So let's take a look at this graph and see what this means. So I have the graph here. This is f of x, right? And let's say we have 1, and then it's up to 7. Okay, 1 to 7. Okay, now if we estimate the value of this definite integral from 1 to 7, f of x dx, that means we are trying to find the area under the curve from 1 to 7. That means we are trying to find the area of this region. So this notation represents for the area under the curve, or this area under the curve with the x-axis between the point 1 and 7. So we want to find this area here, and this area here represented by this definite integral. Okay, so that's how the meaning of this one. But in fact, sometimes we do have the value f of x to be negative. So let's take a look at that case. So when f of x is bigger than 0, then we have something like this. So imagine we have this function, and this is 0, and this is some negative 1, and so on, right? 2, 3, 4. Now, for example, I have the curve to be somewhat look like this. Okay. So, if f of x is negative, then, for example, this point is maybe 8. So we have 0 to 8, f of x and then dx. So this estimation of the formula is actually also the area of the curve of that curve and the x-axis. So which is this one, right? We always count from the curve to the x-axis. So again, from 0 to 8, and the area from the curve to the x-axis in this case. Or you can write this as, so we have a to b f of x dx. This one equal to the area between curve and x-axis from a to b. Because the area is the positive value, so we have the positive value of the area. But then because this one is under the x-axis, we get the negative value for this one. So this notation is actually the negative of the area from the curve to the x-axis. So that's how that's meant. Okay, let's go to another example. Okay, so let's go over this example. This is a really nice example. I have the graph and -1 to 1, and here's 5, here's 9. This is the curve, go to 5 and then you go up to 9, and this is y equal f of x. This is x. So you want to rank the following quantities from least to greatest, or smallest to the biggest value. Okay. I have -4, I have 0, I have 4, I have 0 to 5, f of x dx, and 5 to 9, f of x dx, and 0 to 9, f of x dx. Now, we have 1, 2, 3. So these 3 values we already know the true value, but we don't know the value of this one and this one and this one. So we cannot compare to the given 3 value here. So the first thing is, let's try to have the an estimation of this definite interval, this one and this one. So in order to estimate the value from 0 to 5, or we are just finding the area, right? The area of the function f of x between 0 to 5. From 0 to 5 here, right? Which means the area of this region. And remember, in order to estimate for the area, we have to find a rectangle, right? The rectangle, the height multiplied by the width. But in this case, let's see, we cannot estimate this using this curve, but instead we can draw 0 to 5. We can draw this rectangle here, right? We can draw from 0 up to 1, 1 to 5, and here. So this area under the curve can be estimated using the rectangle from 0 to 1, 1 to 5, and then go back to here. So we can use this rectangle to estimate. We assume that we can have a good estimation for the region we want to, but we don't have enough information. However, it looks like that this region that we want to find the area is very close to the area of the one I just draw here. So this one is 5 for the width, and the height is 1. So 5 times 1 give me 5. So imagine we can use this rectangle to represent for this value. So maybe it's 5, right? Some estimation. Now from 5 to 9, which is the value of this region. But remember, it has to be a negative one. Okay, it's under the curve, the x-axis. Now we can draw the rectangle here and do the estimation. So from 5 to 9, it's 4 units, 4 for the width, right? And the height is just 1, right? From 0 to -1 here. So 4 times 1 is 4. But because we can using this rectangle to represent for this one. But remember, the true value is somewhat smaller than 4, because this our rectangle that I just draw is bigger than overlap, is overestimate of the true value. So some values less than 4, and it should be negative for this one because it's under the x-axis. So it should be -4 for this one. So -4, and this one is 5. And from 0 to 9, we are just summing all the value from 0 to 5 and from 5 to 9. So we have 5. Imagine we have 5 for the first one, -4 for the second one. So 5 minus 4, we sum them, because this one is just a summing from 0 to 5, 5 to 9. Right? From 0 to 9, that means we are counting from 0 to 5 and from 5 to 9, which is 5 minus 4, so we're around 1. Now, we can compare the answer now. So 5, the first one, this one is 5. So we can say that this one is the largest value, right? So the largest value is this guy. So the answer is 0 to 5 is the largest value. And the next one, which one? This one is 4. This one is, so 4 is the second value. So 5 is the highest, then 4, right? And then go up to 1, and then go to 0, and then this value here, remember, it should be smaller than -4, so maybe 3 minus 3 something. Okay, so it should be this one, which is 5 to 9, and the last one is -4. This is f of x dx. So this is the highest value, 4, 2, 1, 0, this one, and -4. Alright. Okay. So let's summarize this. So we have -4, 0, 4, and these three iterations. We know the value of minus 4, 0, 4. Now we want to estimate this value so we can compare. This one gives you around 5, so it should be the highest value. This one gives you somewhere between less than minus 4, but this one is minus 4, so this one should be bigger. So I put it here, and then minus 4 the last one. And we have 0, 4, so 4 of course is higher, the next highest value after the first one. And this one is 1, so of course it's bigger than 0. So I have 1, or in this case I should write 0 to 9. Sorry, 0 to 9 is a 1, that gives you around 1, and then the next one is 0. So you can, this one you can use this notation. This one bigger than this one, bigger than this one, bigger than here, and bigger than here, and it should bigger than here. Okay. The last topic here: if the function f of x less than g of x for a from a to b, then the area between f of x and g of x for a x less than b is from a to b, and f of x minus g of x dx. Okay, so we have another definition. If the function f of x is less than the function, sorry, it should be bigger than the function g of x from a to b, then the area between f and g should be f of x minus g of x multiplied by dx from a to b. So if you draw out the function, okay, I have this is f of x, and somehow this is g of x, right? F of x is bigger than g of x, so this is higher than the g of x. Now from a to b, that means we are considering the interval from a to b. Therefore, the interval from a to b of f of x minus g of x is the area between f of x and g of x. So the area between the two curves, we take the higher value minus the lower value. We got the area between the two curves from a to b. It is represented by this definite intervals. Okay, so the definite interval from a to b, f of x minus g of x is the area between the two curves. And we'll go into more details, more example in the class next week about this.